Hello, my talk today is on non-hydrostatic modeling of flow interactions with highly flexible vegetation. My collaborators are Ramin Famil Khalili and Gongfeng Ma. Why are we interested in vegetation flexibility? It is important because vegetation motion affects wave dissipation rate. The higher the vegetation flexibility, the lower the dissipation. Vegetation motion also affects current profile. It determines how deep a flow profile vertically penetrates into the meadow. It also affects the turbulence-induced sedimentary suspension, as well as sediment transport. On the ecological side, vegetation motion determines seagrass orientation and therefore determines the light absorption by vegetation or seagrass elements, for example, and determines seagrass production. Again, on the ecological side, the impact of vegetation motion on the flow and wave determines what the residence time, which is important for larva distribution as well as seagrass seed dispersal over a meadow. There are many numerical wave vegetation interactions used over years. In the past decade, most models can be categorized into Reynolds-Averaged Navier-Stokes or RANS models, as well as Boussinesq models. Based on the vegetation formulation in these models, the recent models can be categorized into semi-flexible or fully flexible vegetation models. The models that are in the semi-flexible category have vegetation mechanisms that limit vegetation motion. For example, Moza et al. 2013 and Zhu and Chen 2015 are RANS models that fall under this category. In more recent years, there have been attempts to fully eliminate any restriction on vegetation motion in models, and numerical approaches have been developed for this purpose. And these models that I have listed are the ones that do not limit vegetation flexibility. Chen et al. And Mattis et al. Are RANS models in this category, and work in our group based on Boussinesq models also fall in the domain of fully flexible vegetation. In this study, we expand upon our work with Boussinesq models to use a RANS wave resolving wave model and couple it with a flexible vegetation dynamics model. The wave model used in our study is the non-hydrostatic wave model, NHWAVE. It's a 3D phase resolving model that uses sigma coordinate system. In this model, in this formulation, as you can see, U is the velocity in 3 dimensions. So we have a full 3D system. Here, the background turbulence and the viscosity in the flow is represented by the stress tensor, tau, and the viscosity and form drag are represented by the final 2 terms in the momentum equation, which usually are combined in a drag force, which is parameterized by a drag coefficient CD. So the drag force is a function of drag coefficient CD, vegetation stem thickness B, stem density NC, and the flow in the that is applied on the vegetation stem. The vegetation stem dynamics model is a numerical and pendulum model developed by Zeller et al. In this model, essentially, stem is discretized into n segments, which are connected via joints, and those joints are equipped with torsion springs and rotary dashpots. The torsion spring coefficient represents the rigidity of the stem, and it is a function of the segment geometry as well as de Young's modulus. Okay. The rotary dashpot only dampens the numerical oscillations, does not have any physical representation. On each segment, we have a comprehensive set of forces, including buoyancy, gravity, drag, lift, friction, and inertial force that combined with the forces applied at the end of each segment will form a system of differential equations over the entire stem that will be solved simultaneously, and the output of this model will be the orientation of each segment as well as the forces applied by the flow on the segment and by extension in the entire stem. Okay, this is the flow chart that shows the coupling of the two models. The input is provided to NHWAVE. NHWAVE solves the flow and oscillatory and uniform flow if they both exist, and the flow is fed into the flexible vegetation model. Flexible vegetation model computes the orientation and the drag coefficient, which, by the way, are the function of space and time. So the drag coefficient in this approach is not a constant. Okay, these two will be updated in the input that is fed into NHWAVE, and the process continues until the simulation concludes. This slide shows typical results of the model. Here we have a wave with 5-second period and 10 centimeter amplitude, and current with 5 centimeter per second intensity. As you can see, we can simulate numerous stems. So a meadow of 40 meters can be simulated in our using our model. And the model is capable of simulating the whipping motion under wave and current condition. And this stem that I'm showing is the first stem in the middle. Okay. So next slide shows the comparison between the model and experiments of Moza et al. 2013. In those experiments, 5 stem bunches were aligned in a flume, and the maximum and minimum orientation of each stem were documented. Here, the solid line shows the model and the dashed line shows the experiments. And as you can see, over the 5 stems, our model does a very good job in simulating the stem orientation. As I mentioned, in the modern models that are used for wave vegetation interactions are generally based on Boussinesq or Reynolds models. So it is informative to compare these two types of models as their for their performance in terms of the impact on vegetation. Here I'm showing the stem forces over a wave period as applied, as computed by NHWAVE and Boussinesq models. As you can see, the Boussinesq model overestimates force in a stem. In this example, for Boussinesq model overestimates the maximum force by about 50%. As for the orientation of the stem, NHWAVE simulates the vegetation stem very closely to the observed experiments. Whereas the Boussinesq model has a larger deviation. In our scenario here, the RMSE of the Boussinesq model is about 37 centimeters, whereas the RMSE of the NHWAVE is only about 1 centimeter. One advantage of the advanced model is that we can simulate the interaction of the flow with the vegetation. Here I'm over the entire water column as where there is a strong variability in the vertical water column. Here I'm showing in the top the interaction of the flow with the rigid vegetation, and at the bottom the interaction with flexible vegetation. Flow properties and vegetation density is the same in the two simulations. Here I would like to point out two distinctive feature between the two types of vegetation. Over the rigid vegetation, we have a higher dissipation of the flow within the middle as expected. Whereas for flexible vegetation, you have higher velocities within the middle. Another distinction is the flow at the interface of the middle and the free water above the middle. As you can see, we have intensified velocity at this point, which is not observed over rigid vegetation. Okay. In the next slide, we compared the flow velocity, wave averaged, the entire profile with the conditions of no vegetation, rigid and flexible vegetation. Okay, so here I would like to point out the aspect of the flow that I mentioned in the previous slide, which is a strong flow over near the interface of the flexible vegetation and the water above. Okay, so as you can see, that increase in the flow profile exists also in the rigid vegetation. However, that peak is more pronounced when we have flexible vegetation. In addition to that, the peak is further into the middle, so the peak is lower as compared to the rigid vegetation. These differences in these processes over flexible vegetation is what we are exploring currently more into detail. So in conclusion, our model compares very well with the data for stem orientation, and we showed that the Boussinesq model overestimates the internal forces in vegetation stems, possibly because of the inherent assumption in Boussinesq model where based on weakly dispersive assumption, we have a relatively uniform flow all the way to the bottom, and that can cause possibly higher drag force at the base of the vegetation. NHWAVE shows a superior performance compared to Boussinesq model for stem orientation. Right now, we are validating our model for wave dissipation, flow profile, and stem forces with the published data in the literature. With acknowledging funding from Jeffress Award, I conclude my presentation. Thank you very much for your attention.